Okay, I'm quickly going to go over the sort of first principles definition of the derivative and how we can come to that conclusion. So we're just going to have like a sort of general function here. Doesn't really matter what it looks like. I don't know if you can actually even write this as a function. And the whole point of a derivative is to find find the gradient at a specific point on a curve, like an arbitrary function. Let's just say this has a point x. So we can have f of x, and we want to find the gradient of the function at this point. Obviously we don't really know how to do that, but what we do know how to do is find the gradient of a straight line. So let's go to another point on the curve at another arbitrary point on the curve. So let's just say this is at x plus h. It's going to have y coordinate h. And actually finding the gradient of this straight line, finding the gradient of straight lines is really easy. It's just the change in y over the change in x, and we know how to do that. Well, we can just use our diagram. So the change in y is this this part of the line here. So that's just going to be f of x plus h minus f of x divided by the change in x, which is just going to be x plus h minus x. That's the distance between these 2 points. And as you can see, these x's are going to cancel out, and we'll just be left with, because we have x minus x, so we're just left with the h on the bottom. So this is the gradient of this straight line, this arbitrary straight line between 2 points on the curve. But what we're interested in finding is actually the gradient at this point. So that's, and h is arbitrary, so could have had h be here, then we'll have this, we'd have a line, straight line like this. Actually, as h gets smaller and it gets closer and closer to x, our fixed x, it's going to get closer and closer to the gradient of the curve at the point x. And so when this gets infinitely close to x, that's going to give us the gradient of the curve at x. So this is how we define the derivative. So we use this f dash x equals, so as h gets smaller and smaller, it gets closer and closer to x. So we'll write this as the limit as h gets smaller and smaller and gets to 0. As it comes to 0, this gradient of this straight line will give us the gradient at the point x on our function. So we just copy in what we've already figured out. There we go. That's the limit definition, first principles definition of the derivative. Let's actually use this to do an example quickly. That's not copied at all. So let's just copy this and quickly use this to verify some derivatives that we might be familiar with. Let's just put that in the corner, and let's think about if our function was, say, just standard quadratic, just x squared. Alright, so let's figure out the derivative, the gradient, the general gradient of a point on the curve x squared. So we just have to use our formula. So this is limit h goes to 0 of f of x plus h, but f of x is just x squared, so we're going to have x plus h all squared minus f of x is just x squared divided by h. Okay, scroll down. We just need to simplify this now. So let's expand this. So as you can see, so we have an x squared and a minus x squared, so we can get rid of those. Rip. And then we're just left with this this expression. So we can just divide through by h. Divide this by h, which is gonna give us 2x, and divide h squared by h, is gonna give us h. So we're left with the limit, so h goes to 0 of 2x plus h. Then basically we just sub in 0 for h, right? H is going to 0, so this constant h, this is not constant, this h is just going to disappear, equals 2x. So we're left with that the derivative of x squared is 2x, and that makes sense. That's great. That's the end of the video.